This is the 6D Requs Software Failure Mode Analysis, which improves effectiveness of the ISO 26262. A software failure mode and effect analysis supports this standard by providing a structured approach to identifying and mitigating software-related risks in safety-critical systems. By analyzing the software architecture and identifying potential failure modes, the Software FMEA helps to ensure the safety requirements are met and the system can handle unexpected situations. Shortly, we're going to see how the 6D Requs Software Failure Mode Analysis supports this. Our company has the world's largest database of software failures analyzed by entry point and by root cause. You can see the profile to date of all those failures based on the entry point. You can see the biggest category is design at 31%. Most of these were due to the fact that the software engineers failed to do a complete design. They went straight from specifications to code. Skipping design is a design-related root cause. They tried to write code without having a design in many cases, or the design was incomplete and in some cases was inconsistent with the requirements. Next is code. Coding-related entry points means the design was in place, the specifications were in place, but the code that was written did not comply with what was in writing. Next is the specifications themselves. These are the collection of the software requirements. They might be conflicting, they might be ambiguous, they might be missing. It could be there's unwritten specifications, unwritten assumptions. And then next was the interfaces. These originate in the interface design specifications, and these are due to what is not in those interface design, as well as conflicts in that interface design. Most of the interface-related root causes occurred between two software components written by two different organizations. Finally, last on the list, we have the single shall statement. That means one individual requirement, 6% of the time, contributed to a total software failure. Okay, code analysis tools like Fortify, Coverity, and LZRA, they are oftentimes more effective than humans at identifying the defects, largely because of the massive amount of work it takes to review the code. The 6D structured approach identifies the other 71%. When combined, those two methods can provide more complete coverage for identifying root causes of hazards. Now let's look at the root causes. What we've analyzed, we start at the top: algorithms, state-related issues. Error handling means the software fails to detect faults in the software or the system. Functionality means it's doing the wrong thing. Processing means it can't handle peak loading or endurance. Timing. Usability means the software actually causes the user to do something that leads to a failure. Data definition was also a big area. The primary example here is the metric English defect that was seen on the Mars Climate Orbiter. We have sequencing at 9%, algorithms at 6%. The 6D approach ensures that all contributors to software defects are considered, not just a few of them. Okay, let's take a look at how the 6D Requs Software Failure Modes Effect Analysis works. These are the 6 dimensions. The first dimension is the software itself. The second dimension is the electronics. The third dimension is the system, comprised of all the subsystems and parts. The fourth dimension is the user. The fifth dimension is trajectories over time. Trajectories means the state of the system or the values as a function of time over the life of the software or over the life of the mission. And 6D is related to a variety of environments for which the software will be operating. Let's see an example here. This is an example of an update for a vehicle software. One example of a 1D root cause, the software update isn't designed to handle interruptions. Example of 2D, the update doesn't check if the subsystems are in a ready state prior to the update executing. Example of 3D, the software assumes that the vehicle is in a particular location for the update and allows that update when really it should not. 4D, the software allows the user to update when their device isn't fully charged. That could lead to it being disconnected in the middle. 5D, the software cannot handle the case in which the update isn't executed when available and before the next update is available. So basically, because they skipped an update, the next update tries to update and it's not able to. 6D, the update is enabled when the vehicle is in the shop for other repairs. What will happen there? The update might execute when someone's actually working on the vehicle. Without the 6D structure guidance, people will overlook hardware faults, system faults, user interactive actions, valid trajectories, valid environmental scenarios, and they'll overlook them when specifying, designing, and testing, which is a key part of ISO 26262. The 6D Requs has a list of root causes for each dimension. Now, the specific ISO 262 methods that are more effective with this 6D Requs FMEA, these are just a few of them. The 6D approach provides a structured list and a structured process for working through what can go wrong. This is essential for the hazards analysis of risk assessment, identification of functional safety requirements, and design and test. These are just a few of the methods that are improved with the 6D Requs Software FMEA approach. Error guessing is based on individual expertise. That's great, but many times the experts don't know all of the possible things that can go wrong. They may think of the things they have seen when really there's other things that could go wrong that they're not familiar with. So this gives them a complete list of things that can go wrong. Control flow monitoring is more effective when the states and models are analyzed in a structured fashion. And fault injection testing is more effective when based on a software FMEA that analyzes a structured list of things that need fault handling as opposed to a more ad hoc fashion. So for error guessing, we have a complete list of 187 historical causes of defects that facilitate the error guessing. These are published on the Common Defect Enumerations on the DAU R&M Community Practice website. Control flow monitoring. Of these 187 root causes, 15 are state-related, and they're often overlooked even when people are thinking about control flow. Fault injection, we've identified 31 key areas that need fault detection, handling, and recovery. By looking at the structured list, the software group will be able to consider a more wide coverage of things that can go wrong. Now, how effective is it? Well, the good part is this approach, when conducted by a multifunctional team, can be done in as little as a few weeks. And in that short period of time, the group can analyze up to 188 potential root causes that have historically caused failures in mission and safety critical systems. When you combine this approach with the code analysis tools, you have two highly effective means to identify root causes in software that cause safety and mission critical hazards. About our company, like I said, we have the world's largest database of software failures analyzed by root cause and entry point. We also have the largest benchmarking study. We have measured 679 development factors against hundreds of software-intensive systems, and we have correlated them against actual defects found in operation. We authored the common defect enumeration on the DAU R&M COP website. We invented the first machine learning model to predict the number of defects before the code is even written. We invented the 60 Requs Software FMEA method. And the founder, Anne-Marie Neuffelder, is the current chair of the IEEE 1633 Recommended Practices for Software Reliability, and she wrote a large part of this document.